What is up, everyone? Welcome back. So on today's agenda, all we have to look at are two things. First one of which is the NORAD two-line elements, and then we're going to talk about ground tracks. So let's dive in. So we're now at section 2.8.3. We are finally over with the orbit determination techniques. Whew, that was a lot. We survived. So let's jump into NORAD two-line elements. Or TLEs for short. So if you remember what we did last time in terms of orbit determination, we derived mathematical methods to convert ground-based measurements, position velocity vectors, or two position vectors, and turn them into orbital elements: semi-major axis, eccentricity, inclination, radian, argument of perigee, and time of perigee passage, TP. Now, this is all good if you are a big organization like NASA or the US Air Force or the European Space Agency, and you have access to a network of ground stations around the world that can easily track and monitor any satellites that happen to fly over the ground station. Now, if you are just an end user of those data being created by those big organizations, it would be still nice to have a way to know what are the orbital elements of any spacecraft out there, say the ISS, or in Canada, RadarSat-2, for example. Okay? Turns out those big organizations like NASA and US Air Force are kind enough to publish all orbital elements of every object being tracked on orbit. And the way that those organizations publish those data is through the format called TLEs, or two-line elements. Okay? So this is freely available to all of us. All you have to do is to go to a website, which is www.celestract.com/NORAD/elements. Okay, so just go to this website and you'll see a big list of all satellites being tracked on orbit by those organizations, for which they provide the associated orbital elements at a given time of the last measurements. Okay. Well, NORAD, by the way, stands for North American Aerospace Defense Command, which is a military organization in the United States. And the way that those data are being published on this specific website is that they organize it in two lines, okay? Hence the name two-line elements. And this is a very standardized form. So if you look at, say, RadarSat, which is a Canadian remote sensing satellite, we're going to go to the RadarSat-2 entry in the big list. And right underneath, you're going to see two lines with their number. Number 1, number 2. And you're going to see a bunch of data along line 1 and a bunch of other numbers in line number 2, like that. I'm not going to go over all the details of each entry contained in those two lines, because some of them are way beyond the scope of this course. But for example, the first entry here is the satellite number. So for RadarSat-2, it happens to be like 32,382, probably related to the number of the launch for this particular satellite. Next to it, we have the international designator, which is 07061A. Okay, that doesn't really help us. It's good to know, but that's not what we are interested in too, right? What we'd like to know for this particular spacecraft are its orbital elements associated with its current orbit at a given time. So for this, we need to go through the entries, and ultimately we're going to hit a first term of interest, which is on the second line, third entry, we are going to get the inclination directly in degrees, okay? Next to it, the fourth entry is going to be radian, followed by eccentricity. Immediately after the sixth entry of the second line is the argument of perigee. The seventh entry is the mean anomaly, and remember that this is simply the mean motion of the spacecraft times time since its last perigee passage, t minus Tp. Next up is the mean motion n, and that's about it. So based on these 6 entries, it will be up to us to convert them into what we want. So we have already 4 orbital elements directly provided to us. Then from here, the mean motion, we can easily extract the semi-major axis because we know the relationship between n and semi-major axis A. And then with n, we can come here and solve that relationship for what we consider to be our 6th orbital element, which is time of perigee passage Tp. So plug n back in here, and T is actually provided along the first line. The fourth entry here will be the time. But the time provided here is not directly in second. You have to convert it because it is provided in terms of days, hour, minutes, and seconds. And I gave you the math to do it properly in the printed version of the lecture notes. Okay? So this is very convenient for end users of ground station data or of big organizations that do make those ground-based measurements in terms of radar measurements or laser-based measurement to figure out the orbital elements of any spacecraft at a given time. Okay? So again, just go to this website. There's a problem in section 2 that I'm asking you to just give me the latest up-to-date orbital elements of the ISS. So we have to navigate to this website, find the ISS entry, and kind of decode all the numbers that are given to you and turn them into useful data, or in other words, into orbital elements that we can then use for practical purposes, which would be, for example, to simulate the ISS orbit in MATLAB Simulink. So again, we'd have to go through the process of turning orbital elements into R and V at any time, and then initializing the integrator blocks this way. Okay? So this is it for 2.8.3. So let's now talk about another useful tool that is extensively used for ground operators working in ground stations, where ground stations are there to establish communication with spacecraft flying in the vicinity of the ground station. So as soon as the spacecraft rises above the horizon, as visible by the ground station, flies over, and then goes back down below the horizon on the other side of the station, while the station's objective is to maintain communication with the spacecraft for, say, telemetry purposes or just for health monitoring of the spacecraft, or to upload new commands for the spacecraft to be doing its next kind of propulsive maneuver, for example, things like that. So all this is handled by ground stations. And the way that ground stations are able to monitor at any time the position of any spacecraft in their vicinity is through the use of ground tracks. Okay? So hopefully you've all seen ground tracks in movies or whatnot. So a ground track is essentially a projection of the Earth in a flat map. Okay? This projection is known as the Mercator projection, and kind of unroll the spherical Earth and turns it into a 2D map. showing all the continents: North America, South America, Europe, Africa, Russia, Asia, Japan, Australia. I'm very good at drawing, I know. And this map is actually has labels for latitude along this axis and longitude along this other axis, with the equator going through the middle here. Okay, so this is the Mercator projection of the spherical Earth. And then what they observe for a given spacecraft is its trajectory or its path as seen from this kind of point of view of an observer which has been static on the surface of the Earth or ground station. So if we are in Ottawa, our current location is typically indicated on the ground track or the map here, and then we would observe the path of the spacecraft with respect to the continents and geographical locations. Okay? So that would be for one complete orbit of a spacecraft orbiting the Earth, but because the orbit is inertially fixed, it means that because the Earth is rotating underneath the inertially fixed orbit, it means that we're going to see this ground track shifting westward, okay? Because the Earth rotates towards the east, which means that the ground track, which is inertially static, would be seen moving in the opposite direction. So that would be, say, first orbit of a given spacecraft. And then the second orbit would be, well, they need to join. So it's not that accurate, but anyway, the second orbit would start a little bit more to the left. I'm doing something like this, and flying right over Ottawa for this orbit. And then the next orbit shifted a little bit more to the left, like this, and then the ground station here in Ottawa would have then lost sight of the spacecraft by then. So the paths, successive paths of the spacecraft, seen from a fixed observer, geographically speaking, is known as a ground track. Okay? So in order to draw the path here on this map, we need to define a new reference frame which is fixed with respect to the surface of the Earth. Okay? And that other reference frame is known as the Earth-centered Earth Fixed Reference Frame, ECEF for short. So those of you that have completed all problems in section or in chapter 1 would already be familiar with this reference frame, but for completeness, I'm going to give it to you. So we have the Earth centered Earth fixed reference frame. Or ECEF. Okay, so now we've seen the ECI reference frame that was centered at the Earth with its X unit vector pointing at Eris as a distant star, Z through the North Pole, and Y completing the triad in the equatorial plane. We've also seen the perifocal reference frame. It has its X unit vector in the direction of the eccentricity vector, its Z vector tangent to the orbit specific angular momentum vector, so perpendicular to the orbital plane, and PY completing the triad. And now we have the third reference frame here, ECF, which is centered at the origin of the Earth, or the origin of this reference frame is at the center of the Earth. Same thing. It has its X unit vector F yeah, fx unit vector pointing at 0 degree longitude and 0 degree latitude. We have fz, which coincides with iz, so it is along the Earth spin axis towards the North Pole. And then we have same old, the y unit vector completing the triad through the cross product of z and x, like this. One thing to remember, and this is quite important, is that unlike ECI, which isn't fixed to the Earth, because ECI always points at the same location regardless of the rotation of the Earth, but this one is actually fixed to the Earth. So geographically speaking, it is fixed, meaning that as the Earth rotates, Fx also rotates with the Earth, okay? So graphically, this is how it would look like. We have the Earth as a sphere. We have the center of the Earth, the equatorial plane, like this. Let me draw the inertial reference frame for completeness, which had IZ towards the North Pole, like that. This is the rotation of the Earth, 2 pi radians per day. This is IX, pointing at a specific star, the vernal equinox, like this. This is the vernal equinox direction, essentially. And IY, that was completing the triad. Now, this reference frame, in terms of orientation, was independent on the Earth's rotation about its spin axis. IX would always point at this direction, okay? But now, for ECEF, I'm going to draw in red, this is different, okay? So we have FZ exactly the same as IZ, but the difference is that here, the X direction of ECF, this one always points at a specific point on the surface of the Earth. That specific point is 0 latitude and 0 longitude. Or in other words, this unit vector with respect to Ottawa is always the same. The offset between this and say if Ottawa is here will always be the same. So Fx does rotate with the Earth, okay? So that the angle between Ix and Fx is time varying. At some time in the future, Fx will become equal to Ix. It is actually equal to Ix once per day. And then the day after completing one full revolution, Fx will begin again to be equal to Ix, and so on and so on. Now, the angle between Ix and Fx is denoted by theta GMT. Okay, theta GMT. So this is known as Greenwich mean time. This angle varies with time throughout a day. So it ranges between 0 and 2 pi in one day. In other words, this angle, so it starts at 0, then increases all the way up to 2 pi in 24 hours. And the way to calculate the current angle, theta GMT, is to take the angular rotational speed of the Earth, denoted by omega plus denoting that this is for the Earth. Okay, so this is your 2 pi radians per day converted to radians per second. I'll let you do the math to convert days in seconds. Times the time elapsed from some initial time. That initial time is arbitrary. It just means that this angle you're going to get will be the angle between your initial time and the current time. It doesn't matter again because the relationship is done through a constant scalar here. Okay? So this is our ECEF reference frame, and I didn't wrote it down, but essentially you have F, Y that completes the triad, and then the angle between IY and FY is also theta GMT. Okay. So now that we have our ECEF reference frame defined, then we are ready to look at how can we calculate the path of our spacecraft as seen from an Earth-fixed point of view. Or how can we draw the ground track on this Mercator projection? Well, this is not too difficult because if we have the position components and the velocity components in ECI, X, Y, Z, all we have to do is to convert those into ECEF and plot, and then from the ECEF components, calculate latitude and longitude, and then plot latitude versus longitude on the graph, and we would see those sine waves shifting to the left one after the other, as multiple orbits are being executed one after the other. Okay? So the way to do it practically, well, actually, we don't even need X, Y, Z components of the velocity. All we need is position components in ECI. So first thing, we'll turn them into ECEF components using the proper rotation matrix, which will be, yes, C, F, I, like that. Now, what is CFI? It turns out the relationship between ECI and ECEF is a single principal rotation. We don't need to do 3 consecutive principal rotations back to back. All we need is a single rotation about the Z unit vector to go from ECI to ECEF, right? As seen from the diagram. So again, that would be CZ. And the rotation between ECI and ECF would be about through an angle denoted by theta GMT. So CZ through an angle theta GMT would then give us, multiplied by Ri, would give us our XYZ components of the spacecraft position vector seen in ECEF. I wrote CZ here, but this is equivalent, of course, to C3, depending on which way of writing rotation matrices is better for you. CZ or C3, this is the same thing. And the definition of CZ or C3 can be found in chapter 1 of the lecture notes. So once you have XYZ components in ECF, the last thing to do is to turn those XYZ components into latitude and longitude so that you can then plot your latitude versus longitude and obtain the sine waves overlaid on top of a Mercator map of the Earth. So the longitude, denoted by alpha, will be denoted by alpha, and the latitude will be denoted by delta, like that. So to calculate the latitude delta, you're going to say that this is arc sine of the z component of the position vector in ECEF over the norm of your position vector, calculated either using the ECI XYZ components or the ECF XYZ components. The length of that position vector is not related to any reference frame. Just use what you have available to you to calculate it. So this is the x component square plus y component square plus the z component square, square root of all that. It's going to give you the norm here, or the distance between M1 and M2. Take the arc sine of that. That gives you the latitude. And then for the longitude, alpha, it is going to be either one of the two equations to calculate it. So either arc cos of the x component in ECEF divided by the norm of your position vector, cos of latitude, or 2 pi minus cos minus 1 Rx in ECEF over R cos latitude. And the deciding factor to use either that formulation or this one to calculate the longitude is going to be if the y component in ECEF divided by the norm of R is going to be either equal or larger than 0, or if the y component in ECF over the norm is less or equal than 0. So you do that check and then pick the right equation accordingly to calculate the longitude. And then you just plot longitude or latitude versus longitude, and you should see sine waves moving to the left like that. That would be the first orbit, the second one, and the third orbit. And the reason why this is being shifted is because the Earth rotates as time goes by. Okay, so the Earth is rotating underneath the inertially fixed orbit. That's why we see this westward motion on the orbit. Okay, now if you look at a ground track, an interesting thing about it is that you can deduce what is the actual inclination of the orbit itself just by looking at the maximum latitude that you see with the ground track. Okay, we'll say delta max can be related to the inclination well, it turns out it's thought it was in the lecture notes. The orbital period. Yes, okay, it's there on page 61, sorry. So this is either directly the inclination of the orbit, so inclination of the orbit here equal to the maximum latitude we reach on the Mercator projection or on the ground track. If I lies between 0 and pi over 2, which is the typical case. Otherwise, is going to be pi minus the maximum latitude reach, and that is if the inclination is between pi over 2 and pi. Now you'll remember from before that this corresponds to a prograde orbit, and that would be for a retrograde orbit. All right, just a quick interesting fact about ground tracks. Just look visually at the maximum latitude reach, and that gives you an indication of the inclination of the orbit itself. Because if you would like to go over the North Pole, right, of the Earth, then you would need to have an inclination that allows the orbit to reach a much higher latitude like that, and then that would give you a polar orbit, much more inclined than this orbit, which would be, say, 60-degree inclination, whereas this one would be roughly 90 degrees inclination, so you can reach both poles throughout one orbit. Okay? If you ever work at an organization where they track spacecraft, in Canada there are a handful of them, or if you look on the website, on some websites there are a lot of available freely softwares that would allow you to track spacecraft in real time. It would all be displayed in terms of ground tracks like that. So hopefully today's lecture kind of helps you get a better understanding on how ground tracks are calculated based on the position vector and their usefulness. And again, I would highly encourage you to go have a look at the NORAD Celestrak website and start playing with actual data for spacecraft that are currently orbiting the Earth. So that's about it for today. As usual, I hope you learned something new. Hope you enjoy the process. And until then, I'll see you. Take care.